Okay, so for 5-5, we're going to extend what we know about the LRAM and RRAM, and we're going to see how that plays a role in finding another way to do approximations. And so we're going to look at how that affects something called the trapezoidal rule. And how to use the trapezoidal rule for doing approximations. So going back to what we know about our left rectangular method and our right rectangular methods, we notice that if we have this increasing function here, and we do a left ram, we notice that we have these gaps here. And so we would say that the LRAM is too small, or it's an underestimate or an under approximation. And then if we notice, if we do the same function here, the same increasing function, we do a right ram where the right corners of all the rectangles are touching the functions. We notice that we have this extra here that is outside the function, and so our RAM would be an overestimate. And so you know, we would like to get something that is a little bit closer than that. So if we look at this closely, here's our LRAM, and if we take this point here and we take this point here from our RAM, and if we would just, you know, here's our RAM point, if we would just connect those 2 points. Here's our LRAM. So just connect those 2 points with a straight line, we would end up with something that looks like this. And so if you notice, you can kind of see the blue function come through here. Where the left RAM, the orange corner, was too small, and the R RAM, the purple, was too much. This approximation method we get by just connecting the 2 points on the function with a straight line comes pretty close. And so if we look at this shape here, we've got the shape where we have one set of parallel sides. And so we have the shape of a trapezoid here. And so if we could approximate this with the area of a trapezoid, we could get pretty darn close, a lot closer than using rectangles. And so if you remember, the area of a trapezoid is half the height times base 1 plus base 2. And so if we look at this, the height really means the distance between the parallel sides. So that's really what we're calling height. The base 1 and the base 2 are the parallel sides here. Now, the area of a trapezoid is a lot more complicated than the area of a rectangle, but let's see how this plays a role with the area of a rectangle. Since we're now focusing on this trapezoid here, we notice that the trapezoid is bigger than the orange, so it's bigger. So we know that the trapezoid is bigger than the orange rectangle. That was the LRAM rectangle, and we know that the trapezoid is smaller than the purple rectangle, which was our RRAM rectangle. So it's somewhere in between there. And so what we're going to do is we're going to rely on the Riemann calculator program here to try to figure out if we can get get a relationship between LRAM, RRAM, and trapezoidal value. So if we grab our graphing calculator here and put in the 1 plus 0.5x squared, so we'll go ahead into our program and our Riemann sum, and our f of x is 1 plus 0.5x squared, and our lower bound is our lower bound is 1 and our upper bound is 4. So our lower bound 1, upper bound 4. Number of partitions, it looks like we've got 1, 2, 3, 4, 5, 6. We've got 6 partitions. And let's go ahead and figure out what our left RAM and our right RAM approximations are. So here is our left sum. So our left sum is 11.6875. Okay. Okay, so we've got 11.6875. Let's go ahead and do a right RAM. So we'll change this to a right RAM now. So our right RAM is 15.4375. 15.4375. Okay, so there's our right RAM. So you can see that our left RAM is small and our right RAM is a lot bigger, almost 25% bigger. So let's go ahead and come back and use our trap RAM. So our trap RAM is option 5. And you can see how close those trapezoid segments are to the actual curve. In fact, even with the resolution of the graphing calculator, it's hard to determine that they're in fact different. But we have 13.5625. So that is 13.5625. So you might guess, with one being a little over 11, the other being a little over 15, and this being a little over 13, that since it's in between the two values, let's just try taking the two values and averaging them. So we'll take our LRAM and our RRAM and add them together and divide by 2. So we'll take our 11.6875 and our 15.4375. So we'll get out of this. And so we had 11.6875 plus 15.4375. So we'll add those together and we'll divide by 2, and we end up with 13.5625, which ends up being exactly what that answer is. So we know that the 11.6875 plus 15.4375 divided by 2 ends up being exactly 13.5625, and that's in fact the process that we go through to do a trap RAM. Is we just go ahead and average our we just go ahead and average our LRAM and our RRAM values. To determine that answer. And so that's basically what that says down there. And so if we look at what the book has written down for the trapezoidal rule, here's what we basically discovered, which I think is the easier method to memorize. This is basically the area of a trapezoid. We can see that we have a bases, base 1s and base 2s, and the height represents the delta x, the thickness of the rectangle. This is okay, but it's a lot to memorize. I think this is much easier to memorize here. So working on this one, it's saying that we have the velocity of a bobsled, and in 1 second intervals, and for the first 8 seconds of its run. And we're going to use a trapezoidal rule to approximate the distance the bobsled travels. So the first thing is that we have a mismatch in the units. We've got the bobsled being measured in miles per hour, but the time being measured in seconds. So the first thing we need to do is get our data consistent. So I went ahead and converted everything to feet per second here. And so we're going to use that and this, and then we can determine our displacement in feet. And so if we graph this, then you can see that the y-axis here is for miles per hour. So I'm going to go ahead and convert that as I plot this. So we're at 0, 0. So here's the first point, and then we're at 1, 3. So that's about right there. And then we're at 2, 7, which is about right there. And 3, 12. And 4, 17. And 5, 25. And 6, 33. And 7, 41. And 8, 48. So those are that's the data in miles per hour. So I just use the miles per hour for graphing, and then I'll use the feet per second for calculation. So this left ram then is going to look something like, there we go. The left ram is going to be a height of 0, and then we're going to have a height here, and then a height here, and then a height there. So if you notice, as we're setting up all of these left rams, my rectangles don't look that good, but you get the idea. As we're setting up all of these left rams, the point that we end up not using is that last point, because that last point actually represents the right side of a rectangle if it were being used. So as we, this bobsled it has a nice smooth movement. It's kind of nice and continuous as it speeds up and as it speeds up. And I'm not doing too good of a job drawing it, but it's kind of got a nice smooth movement there as it speeds up. All of those left rectangles start with the first point and go to the second to the last point, basically. So those rectangles then, with all a width of 1 second, that L ram looks like 1 second times first rectangle is 0, second rectangle is, now I'm going to grab the feet per second. So the first rectangle is 0, second rectangle is 3, excuse me, I grabbed the wrong data. The second rectangle is 4 feet per second, plus 10, plus 18, plus 25, plus 37, plus 48, plus 60. So that is the LRAM. And so when we put in that data into our graphing calculator here, there we go. So we're going to put 1 times the quantity, 0 plus 4 plus 10 plus 18 plus 25 plus 37 plus 48 plus 60. We get a right RAM of 202. So that is our, did I say, I said right RAM, I meant left RAM. We get a left RAM of 202. Okay, so let's see what we get for our right RAM now. So if we look at graphing that, and so we'll kind of start from scratch here. Again, we're going to graph in miles per hour. So the first mile per hour is 0. Second mile per hour is 3. And then the next is 7. The next is 12. The next is 17. The next is 25. Then 33. Then 41. And then 48. Okay, so if we're doing a right RAM now, we notice that on our right RAM, the right side of the rectangle starts with this second value. So that's our initial rectangle. And so as we do all of these right rectangles now, we skip the first value, and we're going to accumulate all of these rectangles here all the way up to that last value of that function. So now we have included that last value that ends up being the right side of that last rectangle. So our right RAM here is 1 times the quantity, skipping the first value, which is 0. So we'll start with that first rectangle height, which is 3 miles per hour, ends up being 4 feet per second. So we have 4 plus 10 plus 18 plus 25 plus 37 plus 48 plus 60 plus 70. And so that's our right RAM. So calculating that, we've got 1 times the quantity, 4 plus 10 plus 18 plus 25 plus 37 plus 48 plus 60 plus 70. And so that right RAM ends up being 272. So we have a left RAM and a right RAM, and that's the quickest way to get an idea of our trap RAM. So we'll put that under right RAM. And so our trap RAM then is to take that and make that into a trapezoidal sort of looking thing. And so our trap ram here, I'm just going to do the calculation. Oops. Our trap ram is going to be uh, 202 plus 272 divided by 2. And so 202 plus 272 is 474, divided by 2 is 237 feet. So that's how much we moved in the first 8 seconds of travel, is 237 feet. For this problem, Bren's riding a unicycle back and forth along a straight track, and they take speed data over the course of time. And if you look at the data, you notice that the intervals do not have the same width. So these intervals are uneven. And when they're uneven, then we need to calculate each area of each rectangle separately rather than just adding the heights together. So here's our graphs. We'll set up an LRAM. So an LRAM is getting those left corners on the function. So here's that first rectangle. Here's that second rectangle, which is much wider, and here's that third rectangle to the end of the 60-second interval. So if we notice, this first rectangle has a height of 2 and a width of 10. Second rectangle has a height of 2.3 and a width of 30. And the third rectangle has a height of 2.5 and a width of 20. So we have to do those 3 areas and add them together. So the 2 times 10 is 20 plus 2.3 times 30, which is 69, plus 2.5 times 20, which is 50. So our LRAM is, adding those 3 together, 139. And our RRAM, which is getting the right sides of those triangles on the function. So this would be our first RRAM, our second RRAM, our second right rectangle would look like that. And our third right rectangle would look like that. So now this first rectangle here has a height of 2.3 and a width of 10. Our middle rectangle here has a height of 2.5 and a width of 30. And our rightmost last rectangle here has a height of 4.6 and a width of 20. So doing the math there, the first rectangle has an area of 23. The next rectangle, 2.5 times 30, is 75. And this last rectangle, 4.6. 4.6 times 20 is 92. So our right RAM, adding 92, 75, and 23 is 190. So our trap then is going to look something like connecting these 2 dots and then coming down to make that trapezoid. and then connecting these two dots and coming down to make that trapezoid, and then connecting these dots and coming down to make that trapezoid. And so to find that area, then we're just going to take the 139 plus 190 divided by 2. You could actually do trapezoid, you could actually do the trapezoid equation for each one of these things, also here and also here if you wanted to. So 139 plus 190 is 329. Divided by 2 is 164.5 is the distance traveled, and the appropriate units here would be in meters, it looks like. So that would be 164.5 meters. So at this point then, you should be able to start using your trapezoidal rule on the homework problems for section 5.5.